All right. Well, welcome everybody. Hope you're doing well today. We'll begin with a couple of announcements. The homework assignment that you've got on your plate right now, homework 1, is due on Wednesday. And so if you have questions related to that assignment, feel free to send me an email, or you can give me a call on Teams, or you can give me a call on the phone. I'll be happy to help you out. But I won't be staying up late on Tuesday night, so get an early start is my suggestion. That way, if you do run into problems, you'll have a little of extra time to overcome any uncertainty you might have. All right, so today we're going to continue talking about flow resistance. Remember that in previous classes what we've done has been talking about the Moody diagram for determining the friction factor F. We've talked about some of the physical phenomena that account for the fact that there's resistance to flow, and so these empirical equations we have to use to determine how much friction loss there is. We're just learning more about the conceptual underpinnings for why we do certain things the way that we do, and so we'll continue that discussion today, and then at the end there's an example problem that's kind of a practical application of flow resistance ideas. So this comes from sections 3 through 5 in chapter 7. All right, the Chezy equation is kind of a historical friction loss formula that for the most part people have moved on from, but it's important for you still to be acquainted with it because you may occasionally run across for example, drainage networks that were designed using some of these older friction methods, and so it's helpful to understand a little bit more about what engineers assumed in those days to be able to understand why pipe diameters are sized the way that they are, for example. So the Chezy equation relates a roughness coefficient C to the velocity that would be predicted as water flows through a pipe. And so a lower C value would be considered rough, and a higher C value would be considered smooth, so that if you have a smooth pipe, then water is going to flow at a higher velocity through that smooth pipe. So that's what the Chezy equation assumes. And you'll notice that after this friction factor C, that we've got the hydraulic radius and the slope of the energy grade line under the square root power. So the Manning's equation later made some refinements on the Chezy equation, and one component of that is rather than taking the hydraulic radius to the 1/2 power, that it has a different exponential function in the Manning's equation. We take it to the 2/3 power, as you'll see. But the Chezy equation you can relate the friction factor F to the Chezy C value according to this formula, which is in page 201 of your book. And I think you may have a homework problem where you're asked to determine the C value for a pipe based on a friction factor. And so this is the formula that kind of converts back and forth between those different roughness characteristics. All right, so velocity distribution is caused in a pipe because of the no-slip condition at the boundary between a liquid and a solid pipe material, and the shear stress that's being applied by the pipe to the water as the water is flowing through the pipe. Remember that water has viscosity that resists flow, and so as water flows in this illustration, we're saying, for example, that water is flowing from the left towards the right in the pipe. And if we have laminar flow conditions, according to the Reynolds number, meaning the Reynolds number is less than 2,000, then we could expect the velocity distribution to have more of a parabolic shape. Whereas if the conditions are turbulent, meaning that the Reynolds number is above 4,000, then there would be more of a logarithmic shape, where in the center of the pipe, the velocity is about the same as most of the way to the edges, and there's quite a lot of variability in turbulence, and so this solid, even line just represents an average over time, where the velocity at one instant maybe would be a little bit less than the average, at the next instant would maybe be a little higher than the average, but over time there would be some velocity at the center of the pipe and some distance, but the closer you get to the edge of the pipe, the velocity is lower. And so what's being represented here is the bottom edge of the pipe, here's the top edge of the pipe, and so what we're saying is as you get close to that top boundary or the bottom boundary, that the velocity is dropping essentially down to zero. And that no slip condition says that the water that's in contact with the pipe is moving at the same velocity as the pipe, meaning it's not moving at all, as zero velocity. The water that's right in contact just at kind of the molecular level is held at zero velocity. And so even though the bulk flow in a pipe could be turbulent, it may be that there is a region of water close to the boundary where conditions are laminar. And so there's a layer of laminar flow. And we're going to spend a few minutes talking about that laminar layer because it has a big effect on what kind of friction is experienced by the flow as the water goes through the pipe. It's just simplistic to say, you know, flow through the pipe is turbulent because there are going to be sections of the pipe where the flow is turbulent, but if you get close enough to the edge of that pipe wall, the velocity is low, and so the conditions are laminar there. So let's talk about that in more detail. Now, this diagram is a little bit hard to understand at first, and so I'm going to have it up on the screen for a while here, and I'll also encourage you to go back after class and read what the author has to say about this figure. This is an important figure, so let me do my best to explain what it's saying. The bottom of this figure, so this horizontal axis, refers to the bottom edge of the pipe. And then the top, this is saying center of pipe. So think about in the center of pipe, what we know is true is that's where there's the least resistance. You know, the water is the furthest away from any stationary boundary at the center of the pipe. But at the edge of the pipe is where the water is closest to that stationary boundary, and it's the pipe that's applying a shear stress to the water at the boundary, at the border of the two, where the water and the pipe touch, is where there's the most shear stress. We know that conceptually. So that's what this figure is saying, is your maximum shear stress is right at the edge of the pipe, and then the further away you get from the pipe, the shear stress is reduced. And so you can think of this shear stress is the resistance force per unit area that's being applied to the water by the pipe. And so at the center of the pipe, it's at the minimum. Right at the edge of the pipe, it's at its maximum. So the shape of this curve is going to vary depending on if you have turbulent conditions or if you've got laminar conditions. In laminar conditions, then there's going to be less resistance at a certain distance away from the pipe than if you have turbulent conditions. So you can notice here in the turbulent flow that the shear stress is higher longer than in the case of laminar conditions. But here's the important thing. The whole reason why we're looking at this is the idea of the boundary layer. A boundary layer is like a cushion. It's a cushion where the water is moving so slow that within that cushion the conditions are laminar. Even if in most of the pipe cross-section conditions are turbulent, there's this really slow-moving zone close to the edge of the pipe wall where the flow conditions are calm, quiescent, slow-moving, laminar, where there's just very little flow movement because it's so close to the pipe wall. And so this boundary layer thickness is something that we want to be able to estimate because it's important for us to be able to compare the thickness of that boundary layer to the roughness elements that the pipe is made out of. Remember that if we zoom in on a pipe, we're going to find little irregularities, and it's going to look like mountain peaks where even something like a steel pipe which if you run your fingers across a steel pipe, it feels smooth enough. But on the molecular level, there are big ridges and irregularities on the surface of that pipe. You can feel them with your fingers if you're running it over a rough concrete. And you know that even though the pipe by the naked eye looks flat, if you get and look close enough, it's rough. And so what we're going to want to do is we're going to want to compare how thick is this boundary layer to the ridges and mountaintops of those roughness elements. Okay, so the boundary layer is also called a laminar sublayer. And it's that cushion above the pipe where the conditions are laminar within that region. Above that region, the conditions are turbulent, but below that region, conditions are laminar because, remember this velocity profile? This is what's causing the laminar sublayer, is the fact that if you get close enough to the boundary of the pipe, the water really isn't moving that fast. And so velocity times diameter divided by kinematic viscosity, there's a lot of different velocities in the pipe. There's not just a single velocity in the pipe. We often calculate the average velocity just for convenience. You know, average velocity is flow rate divided by cross-sectional area. You did that in the lab plenty of times last semester. Q divided by A equals V. Well, the V that we use in that formula, that's the average velocity, but there's lots of different velocities. And so we're talking about the velocity close to the pipe wall, which is a low value, and it causes this laminar sublayer. Now, if you have fast-moving water, like if through most of the pipe the water is moving at a pretty good speed, then that means you're going to have a thin, small boundary laminar sublayer. But if the water moving through the pipe on average is slow moving, then that means your boundary layer is going to be thicker. So you'll have a large laminar boundary layer. So here's some different pipe materials, and you can compare the equivalent roughness of these. And so what that means is that if you are going to represent the average roughness of a cast iron pipe, a new cast iron pipe is made out of cast iron, obviously, right? But if we were going to try and glue some sand particles to a perfectly smooth surface, then to have the equivalent roughness to what a cast iron pipe is, then the diameter of those sand particles that you're adhering to a perfectly smooth surface would need to be 0.26 millimeters. So this equivalent roughness, the word equivalent is just meaning, let's say that we had spherical particles, what diameter would they need to be in order to give the same amount of roughness as the pipe in question? So a riveted steel with lots of rivets is going to have a lot of energy loss, and so you'd need to have pretty large diameter sand grains to equate the roughness imparted by that irregular riveted steel. It's interesting to think that there are still a handful of places in the country where they have old wooden pipe being used, wood stave pipe. They would typically put like a copper coil around it to hold the wood segments in place. But I can't imagine that would be too watertight unless you really had quite a lot of workmanship. All right, so the question is, how thick is that boundary layer? There's a formula that's mentioned in your book called the Morris and Wiggert criteria. So here's the formula that Morris and Wiggert came up with. They said, well, if you determine the shear velocity, which we talked about in class on Friday, shear velocity is a way of representing with units of length per time the magnitude of the shear stress. And so it's a transformation where you take shear stress, divide it by the density and the square root, and then it gives you units of meters per second. So if you have shear velocity for a certain flow condition, and you know the kinematic viscosity of the fluid, then you can determine the thickness of the boundary layer with this empirical equation. So we're just saying how thick is the boundary layer. Now, if you have a boundary layer that's really big, so the boundary layer is larger than 1.7 times the height of the roughness elements. So here, the epsilon that's talking about is the equivalent roughness. So if the criteria is if your boundary layer is much taller than those elements, then what you can say is that the roughness of the pipe is completely submerged within the laminar layer. And that's considered hydraulically smooth. So those roughness elements aren't going to have much of an effect on the flow if the turbulent zone is so far away from them. In other words, they're not really causing that much of a problem because they're fully immersed by this laminar layer. But on the other hand, think about these roughness elements. I described them before as kind of like peaks of a mountain. And so now, if the peaks of the mountain protrude into the turbulent zone, then they're going to have a much larger effect on the energy loss within the pipe. So this is just saying if our laminar zone is relatively small compared to the roughness of those elements, then we have hydraulically rough. So there's hydraulically smooth, hydraulically rough, and you'll notice here that the range that they're saying, the greater than and the less than, there's a pretty big range in between where it's neither hydraulically rough nor hydraulically smooth. It's kind of an in-between zone where the effect of those roughness elements is a little bit more complicated to model, but we'll get there. There's just certain assumptions here in the semester that we're going to make if it's hydraulically smooth or hydraulically rough. Certain parts of the equations we use to determine F will be ignored if it's smooth or if it's rough. And if it's not within that range, then we have to consider both terms together rather than just one term or another term. So we'll get to I'll show you the punchline of this setup, not today, but in a future lecture. And it's not that it's a bad thing. Gavin asks, is rough necessarily a bad thing? No, it's not bad. It's just if it's rough, then we can simplify our calculations in a certain way. Okay, so let's practice some of these ideas. We have an elevated water tank, and water is going to be flowing through a pipe at a rate of 12,000 liters per minute. And the required pressure that we need to meet at the building's ground floor is 350 kilopascals. The pipe is 250 meters long, 250 millimeter diameter, and the friction loss is 16.4 meters. And so we're going to use energy equation here to determine the tank height. And it's asking what is the Darcy friction factor. Now you're going to be calculating F here in a way that's a little different than you normally calculate it. In this example, you're told right off the bat what's the friction loss, and so you know H sub F, and you know the pipe length because it says here it's 250 millimeters, and you'll calculate the velocity. And so we're going to back calculate what must have been the F value in this case, and then based on the flow conditions, and so meaning you have to determine the Reynolds number and compare the thickness of the boundary layer to the roughness of the pipe, then we're going to find out what's the thickness of the boundary layer, and we'll go back and look at whether it's hydraulically smooth or hydraulically rough. All right, so I'm going to put you into those breakout groups to work on this one together, parts A through C, and I'll be circulating among the rooms to see if there are any questions. So give me just a moment to put you in those breakout rooms. By the way, if you don't have the lecture notes printed out, when I put you in the breakout rooms, you're no longer going to see this screen. So what you can do is if you push on your keyboard right now the print screen button, like my keyboard says PRT SCR, it's up close to the delete button. So if you push that button right now, then you open up, so I'm going to do it just to demonstrate. I'm pushing the print screen, and then if you open something like Paint, so everybody's got Paint, right? Then you can paste with Control V what was on the screen when you did the screenshot. So this is just a way of, you can save what's on the screen. Let's see if I can crop that. Yeah, so you can save what's on the screen and refer to it later. All right, so if you don't have your notes printed out yet, why don't you do a print screen on this example so you've got it available as I put you in those breakout rooms. Okay, let me just show you some of these preliminary calculations, and let's make sure that we're all on the same page here. The flow rate, we have to take the meters per cubic meters per second. So there's 1,000 liters in a cubic meter, and there's 60 seconds in a minute. So 12,000 liters per minute is 0.2 cubic meters per second. And then the hydraulic radius that we're going to use later, since it's a pipe that's flowing full, we learned in the previous class meeting, that's the diameter of the pipe divided by 4. So the full way to calculate hydraulic radius is it's the area divided by the wetted perimeter, A divided by P. But if it's a circular pipe flowing full, then you can just use D divided by 4. The length of the pipe is 250 millimeters. We know the diameter of the pipe. You need the cross-sectional area to determine the flow velocity, and then the given head loss is 16.4. So when you put it all into the energy equation like this, the only unknown is going to be how high does the water in the tank need to be in order to achieve the pressure of 350 kPa at an elevation of 20 meters. So that's the base of the building is 20 meters above our elevation datum. Let's look back here. So our elevation datum is the base of the tank. And so it says here that Z2 is the base of the building is 20 meters above the elevation datum. And then the water is continuing to flow through this pipe. You know, it's connected to the building, but then it also continues down the road to whatever building is next. And so that's why the V2 isn't 0, is we assume that the water is continuing to flow onward. So I leave the V2 in there. Okay, so I'm going to pause for a second. The things that we're calculating here is find Z1, and then with the given head loss of 16.4 meters, substitute that into the Darcy-Weisbach equation to find F, and then let's use all of that information to find the thickness of the boundary layer according to the Morrison-Wiggert criterion. So I kind of set up the equations you're going to need, and they're in the order that you're going to use them. First, you'll need to calculate the slope of the energy grade line. Then you'll need to calculate the shear stress. Then you'll calculate the shear velocity. And finally, you can calculate the thickness of the laminar layer. And the units of that is going to be meters. You know, you think about the units of this formula, the Morrison-Wiggert criteria. The kinematic viscosity of water has units of meters squared per second. And so remember, the typical kinematic viscosity of water at standard temperature is 1 times 10 to the minus 6 meters squared per second. And then you'll divide that by the shear velocity that you calculate here. And of course, the typical density of water is 1,000 kilograms per cubic meter. So let me pause for a second. I'll let you run some of those numbers. Feel free to unmute and ask a question, or type your question into the chat box if you want to check on an answer, or if there's something you need to ask about. Feel free. All right, so if you want to check what you've done so far, I have the elevation of the tank calculations and also the friction loss calculations that are up on the screen right now. I'll leave them up for a few minutes here. Okay, so we've already taken a look at the elevation of the tank and the friction factor F. Let's go through the boundary layer thickness calculations. Now the first thing that we need to do is calculate the slope of the energy grade line. And the slope of the energy grade line is going to be the friction loss divided by the length of the pipe. So, let me zoom in a bit. So the slope of the energy grade line will be 0.0656, and we get that from the 16.4 meters of head loss over 250 meters of pipe. And I don't know if everybody noticed it in the chat earlier, but there was the question about, in this case, why is it the friction loss is equal to the head loss in total? And so here in the energy equation, the last term on the right, the head loss term, H sub L includes two components. It includes the pipe friction losses and the local losses. And the local losses are the ones that have to do with a bend in the pipe or a valve that the water encounters. And so local losses are a single location or a point in the pipe where there's a reduction in energy because of the turbulence that's introduced at that single location. Whereas the friction losses are distributed across a length of pipe. And in this case, we don't have any information in the problem statement about local losses, and so we assume that they're zero. And sometimes local losses are called minor losses because in a lot of cases, the local losses are negligible compared to the magnitude of the pipe friction. And that's the case in this example. So HL is HF in this case. So that's why we just assumed that the local losses were frictional. So now back to the boundary layer thickness. Once we calculate the slope of the energy grade line, put that into the shear stress equation along with the hydraulic radius of the pipe being diameter divided by 4 and the unit weight of the water under typical conditions 9810 newtons per meter cubed. So we get that the shear stress is 40.221 newtons per meter squared and can use that to determine the shear velocity. Okay, so the shear velocity, remember that we have to use, it looks like I at first wrote the wrong thing and crossed that out. Density is 1,000 kilograms per cubic meter. So the shear velocity is 0.2 meters per second. And now we put that and everything before it into the Morrison-Wiggert criteria. So 11.6 times viscosity, kinematic viscosity, so 1 times 10 to the minus 6th meters squared per second for the kinematic viscosity in the numerator, and then the denominator is the shear velocity. So what you should get is 5.8 times 10 to the minus 5th meters, which is the same thing as 0.058 millimeters. Okay. So any questions about how we calculated that, the thickness of the boundary layer there? Okay. Well, we had an F value of approximately 0.02. Let's go back to a Moody diagram. I think we can find one. 0.02 is the okay, here's a Moody diagram. And I've never actually considered this one before, so we're on new ground, but what is the Reynolds number in this case? So Reynolds number, remember, is velocity times diameter divided by kinematic viscosity. And so let's calculate the Reynolds number here. The velocity of flow earlier what we calculated was 4.07 meters per second. So velocity times diameter. Diameter of the pipe is 0.2 meters, 0.25, excuse me. And we divide that by 1 times 10 to the minus 6th meters squared per second. It was one of those days where I wish we had a convenient whiteboard that I could use in front of you, but I'm just doing the calculations here. So 4.07 times 0.25 divided by 10 to the minus 6th. All right, so the Reynolds number is basically 1.02 times 10 to the 6th. So if we look on the Moody diagram, here is our Reynolds number, 1 times 10 to the 6th, and we need to find the intersection with this Reynolds number and our F value, because what we're going to say is, you know, what is the relative roughness that would have caused this friction factor with the Reynolds number that we have. And so where does the 1 times 10 to the 6th intersect with the F value that we just calculated of 0.02 essentially. Okay, so here's the point of intersection. So we'd go over this 0.001 is the relative roughness. So epsilon to diameter is 0.001, and we know that the diameter of the pipe, that was given in this example. Let's go back to the problem statement of the example. So the diameter of the pipe is 250 millimeters, and so epsilon is 0.001 times the diameter, 250 millimeters. This is going somewhere, don't worry. 0.001 times 250. Okay, so that means that the epsilon is 0.25 millimeters. So we're going to be able to now figure out what the pipe is made out of. Okay, we go back to this table. This pipe has a relative roughness, according to the calculations we just did, of 0.25. So most likely, this is a cast iron pipe. And the example didn't actually tell us what the pipe was made out of, but now that we know it's a cast iron pipe, and we've got the F value, we could calculate what would be the hydraulic situation for a variety of different flow rates. And so if we wanted to put a different Q through here, or if we wanted to find a different pressure downstream, now we'd be able to calculate what's the specific F value that's going to arise for those new updated circumstances. So there's kind of the closing point I wanted to make was that there is a physical interpretation of this F value. If you know the F value and the Reynolds number, then you can go back to the relative roughness and try and determine what the pipe is made out of. All right. So just a reminder that the assignment is due before class on Wednesday. So you need to submit that by 1 p.m. on Wednesday. So if you do have questions, feel free to reach out during my office hours. I'd be glad to help you out. And that's it for this time. I will see you on Wednesday. Have a good day, everybody.